Hi, everyone. Welcome to another round of IRIS-HEP Fellowship Talks. Today we have Kyle, Nicholas, and Sofia. Up first is Kyle. Kyle was mentored by Simone. Simone, do you want to say a few words before we begin about Kyle's work?
Hi, Robert, can you hear me?
Yep.
I just want to say both Carol and I mentor Kyle, and Carol has been the one sort of closely supervising Kyle. So I think it's more fair that if Carol maybe wants to say a couple of words, just to introduce Kyle's work.
Okay, that's fine.
Okay, good. Yeah, thanks, Simone. So, yeah, it's a pleasure to introduce Kyle Feist. Right, he's just started his first year of graduate school at University of Kentucky, and previously he was at the University of Cincinnati. And yeah, during the last few months, he's been working with me to try to optimize the track reconstruction algorithms for a future Muon collider, and he was using the evolutionary algorithms to try to do that. And yeah, he will tell you more about how now.
Great. Go ahead, Kyle.
All right, so right, my name is Kyle Feist, and I did my fellowship project on the evolutionary algorithm for optimization of a track reconstruction at Muon collider. And yeah, like Robert said, my mentors were Carl and Simone Graziano. So what is a Muon collider? Just like any other collider, it takes particles and smashes them together. But in this case, we're using muons, positively and negatively charged muons. And they just get smashed together, and there's a whole bunch of particle products, and those go out and hit the muon collider sensors. The main allure of the Muon collider, though, is explained by this graph down here. So on the X, you see the Muon energies, and on the Y, you see proton collider energies. So at a much lower energy, you get the same process happening. So essentially, you're getting more bang for your buck with the Muon collider. So because of that, there's a lot of interest. There's been many studies as part of the SNOMAS effort, but there are currently no plans to actually build a Muon collider. So the main issue with the Muon collider is the beam-induced background. And this is a result of muon's tendency to sort of decay in flight. So you see down here in the bottom picture, all this black fuzzy stuff, that's actually decay products of the muon. And these decay products will actually go through the collider and hit the sensors. So here in this red circle, this is the main collision region. This is where the two muons would collide, the positively negatively charged ones. So essentially these decay products act like noise for the main collision particle products. And you can see in this top right graph, this is 10 millimeters by 10 millimeters piece of the sensor. And each one of these dots are hits from the beam-induced background, places where the decay products have hit the sensor. And you can see they're everywhere. So this really is a big problem because it makes our data very noisy. So my focus was on track reconstruction as a way of kind of mitigating that effect of beam-induced background. I focused on the seed finding part, so that slide will come next. the current thing that we do is kind of slow, but there was an addition, which is the seeding plus the combinatorial Kalman filter, which is done with the ACTS library, or a common tracking software library. So I'm going to talk a little bit about the Kalman filter. I didn't focus much on this, but it's a part of the track reconstruction. So the idea is you sort of propagate the seed from layer to layer, looking for hits that are sort of on that path. So you just propagate that all the way out to the last sensor. So this is the seeding part. This is what I focused mainly on. So the idea of a seed is you take every possible combination of 3 hits. So there are good seeds and there are bad seeds. So the one in green here would be considered a good seed because it's pretty much in a straight line. So it would make sense that the particle moved through the layers of the sensors in this way. But you can see this rejected seed in the red. That's a bad seed because that amount of curvature, it's not physical. There would be a little bit of curvature just because there's a magnetic field in the collider. But yeah, it's too much to be a good seed. And then in the bottom right here, you can kind of see how the seed is used to fit a sort of trajectory for the particle. But yeah, this whole seeding process is used as an input for the combinatorial Kalman filter, the thing that sort of propagates the seed through the layers. One of the parameters that you can kind of mess with within the seeding process is the collision region. And the whole idea of this is that you draw a line through a pair of particles and you draw that line towards the z-axis. And the z-axis would be the axis where the particles are moving on. And then the r-axis would be the place where the sensors are, like concentric cylinders around the z-axis. So if these lines drawn towards the z-axis fall within the collision region, which is these green bars here, then we say that that's an accepted seed. But if you look over here, you have these 2 seeds and you draw a line through them. It's outside the region, so that would be a rejected seed. What's interesting about the collision region is increasing the collision region will have the effect of increasing the amount of fakes there are. Well, it has the effect of increasing the amount of seeds that you accept from the beam-induced background, but it also increases the efficiency, which is just a way of talking about how well the track reconstruction did. I'll explain a little bit more about what the efficiency is in the next slide. But the idea is that we can use this parameter to kind of reduce the effect of the beam-induced background. So because you increase the amount of fakes and you increase the efficiency by increasing the collision region, this is a sort of optimization problem. So this is the efficiency that I was talking about before. So the efficiency is just the number of tracks matched to a true particle divided by the number of true particles there are. So you can see why increasing the collision region would give you better efficiency, because it's basically just giving you more accepted seeds, which in turn means that you have more tracks that you can match to a particle. But the whole problem with that is you increase the collision region, you increase the amount of fakes, and that will affect something that I've called the score. So I want to minimize the amount of fakes, but increase the efficiency. And this value K kind of controls how much the fakes affect the score. I should say a fake has a definition here. Specifically, a matched track is at least 2 out of 3 hits coming from the same true particle. Otherwise, it's considered a fake particle. So the idea is that the beam-induced background would mostly come from fakes because there's just so much more beam-induced background hits. So again, we want to maximize track efficiency, track reconstruction efficiency while minimizing the amount of fakes to get the optimal score. So to do an optimization problem, I was inspired by Peter Chantain's paper. So what he did was an evolutionary algorithm. So I decided to write my own evolutionary algorithm. The whole idea of an evolutionary algorithm is very much so connected to biological evolution. So you have some population, you assess the fitness of that population, you select individuals from that population, and then you subject that set of individuals to a chance for mutation. And then you just keep doing that selection and mutation process until what you're left with is the fittest individuals. So as far as the code goes of what I did, I took 5 random values, each with its own collision region parameter. And I used that as an input to seed finding, and then calculated that score and sorted the those pairs of parameters and scores from best to worst, selected 2 of the lowest ones to get rid of, and then I did a mutation with some probability. It was 1/10, and that mutation wasn't a large mutation. It was around the order of 0.01, I think. And then added 2 random values back in to make the population 5 again. And then you can just kind of put that back into the cycle. And you can keep doing that for many iterations. So from using my algorithm, I did find a sort of peak where your score is maximized. Right here, it was score maxed at 0.8, and that was at 0.33 millimeters. So that kind of makes sense, right? So this is a graph of the collision region, or the amount of fakes as a function of the collision region. So you can see, like, when the collision region is really small, you have a low number of fakes. But when the collision region is really big, you get a whole bunch of them. And for the efficiency, you see that too. The collision region is really big, you get good efficiency, but really small collision region, you get bad efficiency. And here in the top right graph, this is just an interesting way to kind of see how the individuals evolve over time. They kind of settle closer to these lower collision region values as the generations go on, which is good. That means our algorithm is giving us better and better scores, because you see that the best score is around, I mean, it's a small collision region. And here, the bottom right graph, that's just the showing that the you get a better and better score each time or as the algorithm goes through the generations. It's possible that this the score could be even higher if I let it keep going, but it's a pretty time-intensive process. for the algorithm to run. So in conclusion, I've shown that my algorithm can increase track reconstruction efficiency while also minimizing the fakes from the beam-induced background. And I've also shown, in theory, this could be used for other parameters to do the same thing. Some of the next steps would be to make the algorithm better. So there's all these parameters that I use in the algorithm to actually make the algorithm work. So there's work to be done there. You could also optimize several parameters at once. So just like how in an evolutionary algorithm, there's something called crossover. Since there was only one parameter in this project, crossover doesn't, there's no point in adding it. But if there were like multiple parameters, I could have individuals that had different parameters, and I could sort of cross over and add those different parameters to different individuals and whatnot. And also the combinatorial Kalman filter stage has its own set of parameters, and I could optimize those just in the same way that I did for the seeding. But yeah, there's some resources. I just wanted to say thanks to Carl and Simone for the support and all the information they gave me. And yeah, that's it.
Thank you, Kyle. I see you have a hand raised.
Yeah.
Yeah.
My name is Ponki.
Sorry, I'm having a hard time hearing. Can
Can
give
you
me
hear
one
me?
sec?
Maybe a little louder.
Okay. So I have a question in slide 8, and not slide 8, possibly slide 9, and I wonder what kind, which types of the tracks you are missing from your efficiency. I think the efficiency is already about 85%, and I don't know how you can improve your seeding efficiency for the future.
Recording in progress.
Ooh. Sorry, my audio died or something.
Okay.
Yeah. Could you repeat your question, please?
Okay. In slide 9.
9. Okay.
Yeah. So in the efficiency plot, I think you have 85% of the efficiency for your seeding, and I wonder which types of the tracks you are missing for your seeding, and I wonder also how you could improve the seeding efficiency for the future.
So sorry, there's an echo, isn't there?
A little.
Yeah. So gosh.
I think it's okay.
So if just everybody, except for
So you
Kyle,
were
could
asking
mute.
about how the efficiency is not as high. So there's some tracks missing. That would be because the collision region parameter could also exclude tracks that that aren't from the beam-induced background. There's nothing here that says that every track being excluded is from the beam-induced background. It could also be from actual. It could be from tracks that we want to keep.
So the in this background, take out some the hits from the seeding. So that's why you're missing the original tracks, if I understand correctly.
Go ahead, Kyle. I muted.
Could you say your question one more time?
I mean, I thought the beam-induced background, I mean, the seeds reconstructed by beam-induced background take out some hits from the original tracks that you want to reconstruct from the seeding. Is that right?
Yeah.
Okay. Yeah, thanks for the answer.
Okay, thanks.
Yeah, maybe just to quickly add, Bunky, is that one of the main issues here is indeed that sort of if you leave it uncontrolled, the number of seeds that you end up with, the number of valid combinations that you end up having from beam-induced background, not from real particle, explodes really a lot. Okay, so one challenge here is to really sort of limit the number of combinations to keep the computing resources manageable. And so, like, let me say, just to give you an order of magnitude, right? So if you just don't try to optimize, you just try to create seeds in a sort of very loose way and so on, you end up with algorithms that take one day of CPU time on a single computer to reconstruct one single event. Okay, that's sort of the thing. So you have sort of to tighten requirements to sort of cut down the combinatorics significantly. And how you do that in a way to preserve things that are good combinations and so on, that's sort of where we were exploring this type of algorithms to see if we could find good performance regions where we could still cut the performance time, but keep a good efficiency and minimizing the fakes. So minimizing the fakes in reality here, it also helps in reducing CPU time, which is sort of a hidden variable, which is not shown in some sense here.
Okay, thanks for your comment.
Okay, any other questions for Kyle? Thank you, Kyle. Up next, we have Nicholas. Nicholas was mentored by Gordon. Gordon, do you want to say a few words to introduce Nicholas's work?
Sure. I just want to say it was a pleasure working with you. This was a pretty cool project, fits in a much larger ecosystem. And I noticed there are several other people who are very interested in this ecosystem here. So that's great. Thanks for coming along to see. I hope this work in the end is going to represent a beachhead for a new place where ServiceX data can be made useful. And Nick, again, thanks so much for all the work.
Yeah, no problem. I had a pleasure doing it. All right, so my project was on implementing ServiceX data as a data source for Roots, our data frame. Now, the goal was to create this library, which I've called XDataFrame, to act as a pipeline between experiment data, which is fetched by ServiceX, and an RDataFrame, which is a root analysis object. And I'll cover all these topics shortly. So the use case would be, it's to speed up and streamline the analysis process so that users of this library would look to spend less time downloading files manually and like seeking out things and making little tweaks. And instead they can use this library to take care of it all at once, and so they can work on more important things. Let's see. So ServiceX is a data extraction and delivery service, or data delivery service, created in part by my mentor, Gordon Watts. Provided a dataset identifier and a selection statement, ServiceX fetches and delivers filtered data from experiment data repositories like CERN's open data. Here's a little diagram about the process. It's pretty simple. I mean, not in the back end. And a dashboard of all of the events can be easily browsed on the website. And so an RDataFrame belongs to root, and it's an ideal analysis object. It's used a lot by high energy physicists working on large data sets, and it hosts a wide range of operations to make complicated analysis more simple in code. And this image to the right is it's from Root's class reference page, but it shows how an RDataFrame is structured pretty well and how easy it is to make filters and definitions of data and do all kinds of stuff with data. It also has implicit multi-threading for fast parallel computation, so that if you're working with millions of events, it's being efficiently processed. And so for this library, we have a wide range of technologies used. Of course, there's root, which is foundation of the output object. We have ServiceX for file delivery. I use CMake as the build system because it's a C++ library. Now the MinIO is utilized by ServiceX due to its high performance. It's a public cloud object storage system. And it's the only service like it that's available on every Kubernetes distribution, which is what ServiceX uses. Now, the core of XDataFrame is utilizing the AWS C++ SDK, which is able to manage and fetch files from MinIO. And that's what made this project kind of difficult, because C++ doesn't have a lot of native web downloading capabilities, so I had to do some extra work for that. Now, for a user looking to utilize XDataFrame, the build system is written so that CMake handles fetching and building all of the external dependencies on its own, so you don't have to worry about building stuff from source just to meet a dependency for this. It handles it all in one step. Now, using it, it'll need to be included in a CMake project. That's part of the code that it'll be utilized in. There are two. The one thing it takes as argument is this big string in brackets. The two important pieces are the DID, which is like an experiment ID corresponding to a specific experiment data repository, and then a selection string. It's written in this language called funcadl, which is a bit outside the scope for this presentation. It basically is, I think Gordon explained it before. I don't personally know a bunch about it, but it's a language that you can extract columnar data from a root file. And so it's basically what you're asking, how you want the data transformed when you receive it. And so how it'll look in actual code is just like this. You'll get an RDataFrame, you name the variable, and then you call XDataFrame with that request string, and then you're ready to go with your RDataFrame once it returns. Now, here's a flowchart of how the library kind of works. It's pretty straightforward. So it takes in a request string, and then it utilizes a caching system. So if you've made the same request before, like the exact same request, it will first check. It'll check the cache to see if you've already downloaded the files. Sometimes you can download 2,000 files, and if you want to run your code again, you don't want to download 2,000 files again. But if it's not found, it'll send the transformation request to ServiceX. It'll do its processing and fetch the data, transform it how you asked, and store it in MinIO. And then XDataFrame will wait for all the jobs to finish, download the files, make a file list, and put all the files into an RDataFrame and return it to you. And as part of this, I've created a demo that is in the form of a Docker image that can be pulled from Docker Hub. So, you know, a user can try out RDataFrame without actually having to install it or do anything except pull the image and enter into it. And there's instructions for those in the on the repository README. And so the demo file contains an example request string, and then creates a root canvas, creates an RDataFrame using this library, then applies a few simple filters, draws a histogram, and prints it to a file, basically bringing someone through the whole hypothetical analysis process using this library. And it definitely serves as a useful starting point for someone who just wants to check it out. All right, and so issues and improvements. I was thinking for at least one improvement, it could be the library could be extended to just point to a file containing your string instead of an actual string. But that's just a little refactor that wouldn't take much time. The main issue is the incorporating it into a project. So we've settled on like add subdirectory in a CMake project with you just clone the repository and then add subdirectory, and then it just works. And then we were also thinking that fetch content could also work pretty well. And I was thinking that installing it like to your full system might not be the best way to go, just because it has a lot of potential issues that a user could run into, and that's what I'm looking to avoid. Let's see. So yeah, I think that's about it for my talk. Does anyone have any questions? Yeah. I actually can't hear you.
Your sound's dead, Ben.
So this is amazing. This is so great
Thanks.
seeing
Thank you.
how all these things coming together. So I would imagine this has to be a pure C++ implementation, that the Python, you had to replicate all the Python work. And so I noted that the language in that selection is actually Castle, which is considered a very low-level language that FuncADL generates. Is there any way that this could be married up with any of the Python libraries to take advantage of that?
Probably. Like, I don't see why not. I could, let's see. So like what kind of Python libraries, like being able to be called from Python?
All I'm thinking is that there's a huge investment in Python libraries to take a higher level language and turn it into that Castle with all the parentheses. I mean, I guess you could do it with, if the query comes out of a file, you could have Python over here, take your fancy query, turn it into that really long string, and then read it from the file, and you might have some way of integrating them. But just in terms of usability, I'm sure physicists will barf if they see that Castle string.
Right.
Yeah.
Yeah, I could. Oh, sorry. What?
No, go ahead.
Oh, I was just gonna say I could probably look into how feasible that would be, but the way that it's designed is it's a standalone library, so that extending it like that is pretty straightforward, I think, if you know how to do that.
Yeah, I mean, you could even add the file as a wrapper around that if you wanted, because the file can just be loaded in as a string. And Ben, to your point, that is very much an open question, and I don't really know what the best way is to solve that with C++.
Yeah, and it seems like building it is already onerous enough, and adding like whole Python dependencies, like, no, you'll never get there. So
right, yeah, I don't think that would be viable, but maybe there are other things that could be done, but not that was not in scope for this.
This is impressive enough. Yes,
thank you.
for sure.
Yeah, exactly.
All right. Any other questions for Nicholas?
Again, I just wanted
thank
to
you.
say thanks
Okay.
for the excellent work. And it was a pleasure working with you.
Yep,
on this.
likewise. Thank you.
All right. Thanks, Nicholas. Up next is Sofia. Sofia was mentored by Savannah, and Daniel was connected. He's no longer here. Savannah, do you want to say a few words to introduce Sofia's work?
Yeah, so Sofia worked on the problem of charged particle tracking with graph neural networks, particularly focusing on trying to build rotationally equivariant graph neural networks. So enforcing equivariances or invariances that are expected in your data directly into GNN or other machine learning architecture can be a way to reduce the network size. So this fits into the overall effort of trying to accelerate these types of tracking algorithms on FPGAs or other types of dedicated hardware. So yeah, it was great working with Sofia, and excited for her talk.
Awesome. So yeah, as Savannah said, I was working on rotationally equivariant graph neural networks, and sort of most of this project ended up being focused on more of a literature review and sort of like getting me up to speed with learning about sort of like the field and what was going on in terms of charged particle tracking, graph neural networks in general. So I'm just sort of going to be talking about what I learned, and yeah. So the main problem is, so the LHC is a unique particle accelerator complex that collides protons at unprecedented energies. So in 2025, there's going to be the high luminosity addition onto the LHC, in which it will collect data of increasing complexity at an increasing rate. So the overarching goal is to accurately track the trajectory of particles in charged particle collisions within the HL-LHC detectors. And furthermore, the analysis pipelines of the proton collisions rely on the reconstruction of the 3D trajectories of the particles within the detector. And so this is currently solved by combinatorial optimization methods, but the CPU time to reconstruct the trajectories from the measurement is expected to increase faster than the projected computing resources. So the goal of the research project is to utilize rotational equivariances within the data to construct a graph neural network that would increase the accuracy and decrease the CPU time in preparation for the new addition. And so we decided to use the TrackML data set because of its relevance and usefulness to the project. And for each event, it contains 3D hit position and truth information about the particles that generated them. And this data set is also very large. It has 10,000 events, 1 billion points, and 1 million tracks. And that was also very useful in terms of making sure it was broadly acceptable. And so the TrackML data set is meant to simulate measured particle hits similar to what is expected for the HL-LHC experiment. And so the coordinate system is a right-handed Cartesian coordinate system with the global z-axis aligned along the beam direction. And so that the z-axis is the axis of symmetry of the cylinders of disk composing the detector. And so when a particle moves through a constant magnetic field, it follows this like helical trajectory around the z-axis. And so the magnetic field is usually aligned with the beam direction such that the particle is bent in the xy plane. TrackML also comprises multiple independent events where each event contains simulated measurements of particles generated in a collision between proton bunches at the LHC. And the training data set contains the recorded hits, their ground truth counterpart, and their association to particles and the initial parameters of these particles. And each event can have up to 4 associated files, whether it be hit truth, event truth, that contain hits, hit cells, particles, and the ground truth associated between them. And so how does this configuration then lend itself to a graph? Well, the hits can be nodes and the pairs of hits on the adjacent layers are edges, where if the edges correspond to the true track segments, then the edges can be labeled as 1. And then if the edges don't correspond to the true track segments, then the edges can be labeled as 0. And so then there are 3 stages within graph neural networks. There's graph construction, edge classification, and track building. We were more focused on the edge classification part. But here's a good sort of visual representation of track building, which helped me sort of understand what we were doing. So once you sort of like have two nodes and like you've already established that there's like a connection between them, then you can extend it to the triplet and then extend that to a track and sort of like be able to have like your final track to disambiguate. And so where rotation comes into play in all of this is that the hits are created by each particle to form tracks, and then the tracks are slightly distorted helices with axes parallel to the z-axis, like I said before. And then so instead of using a typical GNN, we can use this new model to learn graph neural networks equivariant to rotations, translations, reflections, and permutations. And it doesn't require computationally expensive higher order representations in intermediate layers, and it still achieves competitive or better performance in comparison to existing methods. And also the model can be easily scaled to higher dimensional spaces. And so just like a brief like overview of equivariant networks. So input features are defined as a tuple consisting of the spatial point and then the features at that point. And then the neural network is then a linear map that maps input data to process data via functions. And we can use this sort of equivariance to get the transformed output by transforming the input function, for example, a linear translation or a rotation. In the picture on the right, it's sort of like rotational equivariance, and like no matter which way you turn it, it's sort of the same graph. And that's sort of why graph neural networks are so useful to us. And so a lot of this project was focusing on figuring out what would be possible, like as I said at the beginning. And since it was such a novel approach to charged particle tracking, there wasn't a lot of like existing literature on the topic. So I sort of like conducted this literature review on sort of like the things that I talked about earlier. And also for me personally, there was a big learning curve with GNNs because I had never like even heard about a graph neural network. So there was a lot of getting me up to speed with the content itself. And then like once I got up to speed, it took a lot of technical effort to get the data set and existing interaction network running. And so by the time that was happening, pretty much the fellowship was nearly over. So we weren't able to get like a lot of like physical results, but I still learned a lot about the field as a whole. And so like looking forward, if we had more time, it would have been wise to like train the GNN to be rotationally equivariant while reducing the time and like increasing the accuracy. And like this is extremely important because each event is generated with 200 pile-up interactions on average, and we need to be able to sort through these efficiently and accurately. And exploiting the rotational equivariance would cut down on the time tremendously. So yeah, that's sort of what would have been cool to do. It's just like there wasn't enough sort of time there. But I just wanted to say thank you to my mentors, Savannah and Daniel. I learned a lot. It was definitely, I feel like I bit off a little bit more than I could chew at sometimes, but I did learn a lot, and I appreciate everybody helping me every step of the way. So thank you.
Thank you, Sophia. Any questions for Sophia? No? All right. Well, thank you to all the fellows for your presentations, and thank you to all the mentors. And that's all we have for today. So thank you all for coming.